It's nice to be here, and thanks everyone for coming to my talk. I would like to share my experience uh, from trying to interface AI with sensing and control applications at LIGO. So, you should accept. Okay. Some glitch here. Let's see. Okay, now it works. Yeah, so our group at MIT, we focus on trying to incorporate the recent developments in AI and in particular related to controls applications and try to interface it with GW instrumentation science. So our group consists of Lisa, myself, and others. So in this talk, I'll briefly, because we have a wider audience, I'll try to briefly mention about gravitational waves and how we detect them and the sort of challenges that we face from a instrumentation perspective when we are trying to detect such very feeble signals. And then I'll give an example of how we were able to do embedded AI and how we were able to build and deploy a neural sensor and an actuator and incorporate it to one of the gravitational wave detectors, and which was one of the first ever application where we, in a gravitational wave interferometer, where we sort of added a neural element into the loop, and then how that led to improvements in our astrophysical sensitivity. And finally, I'll sort of also mention about what I think are some of the challenges that we would like to overcome when we are thinking ahead for the future detectors. So I would like to start with some open questions. Like these are the sort of questions that we try to solve in our group. One is like we hear a lot about reinforcement learning, AI, but we know that our detectors are like they're not static; they change with time. So one question that we try to answer is like whether AI can handle changing dynamics. So is it like something? Can we get an equivalent of model reference adaptive control sort of thing from the world of reinforcement learning? That's one topic. And then we also are looking for solutions that are sort of generic, meaning that should be able to generalize across domains. So something like a multitasking neural network agent is something which we are very curious if that will work or not. And then when we want to scale up and deploy AI on the edge and incorporate it into our system, we would also need like dedicated hardware that can run in real time. So you have to deploy this trained neural network in real time, but we also need to make sure that because of the changing system, we will also need to incorporate it seamlessly. So something with a cloud support, and then it has to also handle heterogeneous data because we have different kinds of sensors, so different kinds of data come in. So these are sort of the things that I'll come back to it at the end of my slide. And yeah, so let's. I'm sure most of you have already know what gravitational waves are, but let me again try to explain. So these are like ripples in the space-time fabric, which travel with the speed of light. And when you have very compact and massive objects like neutron stars or black holes, and when they are in orbit, and then when they try to orbit in spiral around each other, they release energy from the system through these ripples in space-time. And they travel billions of years, like millions to billions of years, and they are very violent at their origin. Okay, and it's like, at least for the first event, we had a couple of solar mass energy getting dissipated as gravitational waves. But when they reach Earth, like after traveling through like all this distance and time, it gets very feeble, and it will cause a perturbation of the order of 10,000 the diameter of a proton. So it is very, very tiny. And when Einstein sort of calculated the amplitude way back, he thought it would be impossible that we would ever detect this kind of signals. But then scientists have been constantly working, like since the 1960s, trying to develop techniques to detect them. And almost like 100 years after Einstein gave his general theory of relativity, we had the first detection. So it's like very exciting time to work in this field. And how do you detect gravitational waves? We use something known as we use a very complicated form of Michelson interferometer, which you are all familiar with. But yeah, so the key that helped us detect is like all these extra levels of I will say like tricks and tips that we were able to incorporate into a Michelson. And for example, like we have to make sure that we are only sensitive to gravitational waves and nothing else. So that means that we have to isolate the instrument from all kind of perturbations. And since we are like on ground, we are subject to different kinds of noise sources. For example, like seismic noise and the ground vibrations, like they cause a lot of disruption. So we have to sort of isolate our test masses using like multiple stage pendulum. So this is one sort of vibration isolation. But then we also need to have extremely large amount of laser light to circulate. So for like we have half a million watt, close to 500,000 watt of laser light circulating between the arms. And you can also see that we have introduced Fabry-Perot cavity within a Michelson. So there are a lot of subsystems and complexities that are added. And from a controls perspective, we would like to, if you want to run the interferometer in its fine-tuned configuration, at least 300 control loops, which control different subsystems that can range from optics, laser, or like vibration isolation. They all need to work together. Okay, and often what we see is like these subsystems are interconnected. So it is sort of a non-linear multi-input, multi-output problem, but we have to deal with it, and we have to sort of control it to detect these tiny signals. So yeah, so in the ideal world, when in the simplest case, you can think of gravitational wave interferometers as some sort of transducers that will convert the GW signal into like a photodiode current or voltage. And then we should be able to, if there was no other disturbance, we should be able to see in the time domain the like the chirp signal. Okay, it should be fairly straightforward, and it would look like this in the time frequency domain. But we know that things are not ideal, and we have noise, like starting from the readout noise coming from the photodiodes, and then that can introduce high frequency noise that sort of makes the signal a bit more noisier. But then at the input side, we can also have the ground motion, because the ground shakes all the time because of ambient traffic. It could be earthquakes, it could be the rough weather, sea, all kind of stuff. So that can introduce more noise. So to sort of keep everything at its best operating point, we need to sort of close the loop. We need to have some sort of a control system that can detect other sort of vibrations and then feed it back and keep the system in its place and make it only sensitive to gravitational waves. But it's not just one system, it's like many control systems that we need to run, and many kinds of sensors and many kinds of actuators that all need to sort of work together. So you can already see how, and then when you introduce these sort of loops, you can always introduce noise sources to all these extra points. So this makes it challenging, and the way we traditionally deal with this is we try to linearize our systems. We try to compartmentalize and derive solutions for each of the subsystems. But we think as we move ahead, we have to tackle the whole nonlinear problem. So that's the whole motivation of trying to use AI sort of techniques. So this is sort of our figure of merit, like sort of our sensitivity curve for LIGO. So you can see that it's in audio band, so 100 hertz to like 5 kilohertz. And then this is our sensitivity, which is in units of strain, which is change in length by the length of the interferometer, which is 4 kilometers. So we are already able to detect change in length of 10 raised to minus 19 meter, which is very tiny if you can think about it. But why should we have such a spectral, like a sensitivity? What determines this sort of shape? That's when we sort of put in all the details. So this graph projects all kind of noise sources that are affecting different frequency bands. And they are a combination of fundamental noise, which is like fundamental in that sense. And the other sort of noise is all technical. So the technical noises are things which if you did a proper job at instrument, like if you had better instruments or if you had better control strategies, we could get rid of a lot of technical noises, and then we could sort of improve our sensitivity at the lower frequency. And these frequencies are important because that covers the initial phase when the merger happens. So it contains a lot of information. And one sort of noise, which is like, it's coming from alignment. So we suspend our optics because we want to isolate from the ground vibration. But then that also, the optics is then susceptible to misalign. So it can actually move in pitch or yaw. So it can sort of be misaligned, and that sort of causes one of like a lot of technical noises. And that's what we are, at least I will talk in my next slide, how that's what we want to sort of tackle in this work. So the basic idea is like, okay, we have all this classic linear and controllers. Can we replace it with a intelligent AI agent? So this is like an exploratory thing that we are trying to see how effective it would be, how robust it would be, and how scalable this kind of systems would be. And yeah, so to test this, we went to another detector, which is called, you might have heard of LIGO, but there's another one called Geo 600. So it's like a 600 arm length Michelson interferometer located in Hanover. And I used to work here as a postdoc at the Max Planck Institute. So so if you look inside, all the optics and everything is sort of isolated in ultra high vacuum, and yeah, they are suspended, and you can also see it. So what we want to do in this work is try to see, let's look at Geo 600, which also functions as a test bed interferometer. So a lot of the technologies that has actually gone into LIGO and other large scale detectors were first tested and then fine tuned at Geo. So it has a very important like relevance in the whole gravitational instrumentation science. So we look at how the optics is, the alignment of the optics is controlled using the traditional technique, which is called differential wavefront sensing. And it's a classic technique, and in this talk I'm not going to go into detail, but so we have this existing technique and we have some, it's not optimized, but it still works. So what we want to do is like try to see if we can sort of augment this existing tech controls with, first we have to sense, right? We have to sense how the things are moving. So we need some sort of a neural sensor which can detect how the optics is changing with time. And then we need, once you sense how much things are moving, we need to sort of control them. So you need some sort of a neural controller. And in this case, for the sensor, we had a combination of CNN and LSTM neural network, because CNNs are good at extracting the spatial features and from the images, and LSTMs are good in terms of like they have a sense of time, and if you want like to control dynamical systems, so LSTMs are very useful. These days you could have a transformer based architecture, so that's also possible. And then from the controller side, what we want is something which can handle multiple input and multiple output. And it has, the system that you are trying to control is a dynamical system, and your actions have consequences. So you need to be very careful. And so we use something known as reinforcement learning. And inside reinforcement learning, so let me talk about reinforcement learning then. So this is like an experience-based learning. Okay, so that's what reinforcement learning is. So it tries to interact with the system. It tries to see how the system responds, and from this it tries to from this sort of output that it receives, it tries to build and then get to get. I'll talk about it in my coming slide, but essentially it tries to interact with the system, see how the system responds, and the user will have provided some sort of a metric, like a reward, which sort of explains how good or bad my action is, and the RL agent tries to maximize by constantly interacting. It tries to maximize the long-term cumulative reward. So this is how the RL agents work, and especially for dynamic, like continuous control problems, because our action space is sort of continuous. The soft actor critic agent is what I found to be quite useful. So let's see. And yeah, so finally, and then once you have the sensor and actuator, you need to sort of deploy on the edge. So you also need to, because we need sort of high bandwidth control, right? So we need to deploy the network into target hardware. So let's see. So, okay, so the images are not that clear, but let's see. So what, yeah, so if you can think like this is our optical layout, and how do you deploy such a sensor? So we know that if you look at the laser field that is coming from different regions of the interferometer, if you can sort of image the field and look at the spatial extent of the field, the misalignments in the optics, you know, how several of the optics are encoded in the light field. Okay, so by looking at the light that comes out from the most sensitive part of the interferometer, which we call the dark port, there is a possibility that we can decode the misalignment of like most of the optics that influence the final final light field. So that's what we did. So we deploy, and after we train, we deploy this CNN LSTM sort of neural network. And because we wanted it to run in real time, we had to quantize the neural network, so which I'll talk in my later slide. And once you deploy, we are able to recover the mirror motion, so which is quite nice. And the thing is, it is less sensitive to the existing differential wavefront sensor, because it's a complete virtual sensor. So it's not subject to drifts or other kind of problems that we expect with the wavefront sensor. So yeah, so let me also talk about. Yes, sure.
Yeah, can you say a little bit more on maybe two things? So one is, in what sense is this a probabilistic model that you're using there? And the other thing is, in terms of, you mentioned reinforcement learning. Can you say a little bit more about? You know, what you trained on and what kind of?
Yeah. So let me come to the first part of the question. So whether it is a probabilistic model. So the one that we implemented, it is not probabilistic model. So it is something that I would like to do, but at this point, it doesn't make a. It just gives a scalar value, so it doesn't give the sort of. But I guess if you go for some ensemble model or something, we should be able to get probabilistic. But in this case, since we are closing the loop, you know, so even if it is probabilistic, I have to think how useful that would be. So
in the end, you have a signal. Or
yes,
you have some data signal. You want to understand it. So
yes,
you want to associate some probability to that background.
that's true.
And so in that sense.
Yeah, so right now I'm not sure if LSTM, like we might need some Bayesian sort of framework, I guess, to make predictions with error bars. But yeah, the LSTMs that I used, we didn't have. So what we do is like, so to compare it, we fine tune our interferometer, we fine tune our existing wavefront sensors, and then we make a golden reference measurement. So that's what I show in the colored graph here. So that's like the ground truth sort of measurement, and I sort of compare my LSTM predictions with that. So that's what I do right now. But yeah, we can think about how to improve it in the future. And like RNN training, like the reinforcement learning training, I'll talk about in my next slide. So yeah, so quantization is something which we really care about, because we ideally, you know, we could train big networks, like they might give us better predictions, but it becomes very bulky, and then we cannot deploy it in real time. So we might be limited first by the memory requirements. If you are deploying on the edge, you are like using a NVIDIA like a Jetson sort of a device to deploy, memory requirements, and also like how many frames can you process in a second. So that's also a constraint if you want to, you know, it's like a trade-off between accuracy and like latency. So quantization is a very nice step where we sort of convert from single bit to int8 precision. So we sort of choose certain layers and try to see if we can sort of quantize, and it's like a trade-off. But if you are satisfied with the level of accuracy that you receive, it's a good technique, and we were able to sort of decrease the size and make it faster without much without loss of accuracy. And then so once you have the sensor, now the controller, how do you train the controller? So as I sort of mentioned, the controller in reinforcement learning is sort of it's called the agent, and the agent is something who can interact with the environment, which is the interferometer in my case. And once it interacts, it changes the state of the interferometer, right? So it changes the state, and the interferometer now goes in a different state. But if I sort of know what's the optimal state which I am driving, I can sort of derive a metric or a reward, which is something like it's a response. It's an immediate response to my action. So it gives you whether the immediate action is good or bad. But the goal of RL is to sort of maximize the long-term cumulative reward. So and then, but the issue here is like you cannot train with a real interferometer in loop. Because in the exploratory initial phase, the interferometer can do, the agent can do a lot of actions which might not be desirable. So it can push, it can sometimes damage the instrument. So we have to be very careful on how we sort of train the instrument, train the agent. So what we do is like we make a model for the optomechanical plant. So what we do is like, so once we have the interferometer, I can make measurements, and from my measurements, you can build a reduced order model. So this will capture the essential dynamics, and it will be lightweight, and then I can sort of train it on, in a cluster and using GPUs without sort of damaging the instrument. So this is one way to do it. It might not be the perfect way because no model is really accurate. Yeah, but that's one of the challenges that we are trying to address. Like, train it on a reduced order model, then get something which works, deploy it, and then fine tune it later. So this actual training might look something like this, where you have a reduced order model, the plant, and then the agent is like the soft actor critic, and then a reward. So in some sense, how do you construct a reward? What guarantees the best reward? So this is a very complex question, but luckily, because we have classical controls developed, across decades, we can leverage upon the classical control theory and then sort of derive the best sort of rewards which can drive the system into the best state. So we sort of use things like LQR and then add all that into our reward function. So so let me just, so this is the sort of mirror that we are trying to control. So it's like a fused silica, very, very fragile signal recycling mirror at the heart of our interferometer. And I'm trying to control the pitch and yaw. And here I compare it with the linear classic controllers, where I have multiple classic controllers, and I look at the error in pitch and yaw, 2 degrees of freedom, and I sort of compare it with the RL agent. So you can see it gets better, but then we also tried using many agents. So you can actually have an ensemble of RL agents, which will all sort of give their inputs, and you can sort of average the decision, and that at least we saw that it improves our result. And let me show some videos. So so this is like a simulation of where we are trying to do the tracking. So we have 2 degrees of freedom, and we are like changing the degrees of freedom, and we are trying to see how 2 separate classic PID controllers are able to track, and we compare it with how an RL agent is supposed to work. So so the nice thing is like the RL agent is a MIMO agent, so it can handle multiple input and multiple output. So, and it can sort of understand the interactions between the degrees of freedom. So that's quite nice. And finally, once we have all the elements, like we have the sensor actuator, we trained it on our reduced order model. So we finally deploy it to our interferometer. So this is the geo layout, and this is the most critical mirror. And if you look inside the vacuum chamber that I showed you, it would look something like this. And we close the loop with the trained sensor, and we sort of deploy it after we quantize the network into a edge AI on edge sort of device, in this case, which was Jetson. And with the RL agent, we sort of close the loop. So this is how we sort of do the thing, and but we have to be very careful. But we made sure that our actions are within the bounds, and so it's a safe way to deploy. Let's see. So finally, we were very happy to see the result of how it turned out. So what we did was, like, we asked a very experienced commissioner to fine tune the interferometer. Okay, and because we have like years of experience, right? And then we asked them to fine tune the interferometer, and then we looked at the sensitivity. So the blue trace shows how many megaparsecs we can see for a pair of binary neutron stars. And then we got the data, and then we switched to the neural optimizer that we deployed, and then we looked across hours, and so that's when all this drift and all these things misalignments would kick in, and it was able to sort of push our sensitivity further. So it's very nice to see this sort of thing really helping GW instrumentation science. But we would like to, there's a paper if you want to read more about this. But so this technically would mean we are expanding our horizon, and we are able to capture more events. So now at LIGO, we want to sort of deploy it at a much larger scale, and we are trying to also answer different sort of questions. We don't want specialized neural RL agents for different subsystems. What we are looking forward is, can such an agent handle multiple policies? It should be able, because all the subsystems are interconnected. We want the agent to sort of optimize the vibration isolation. It should be also do the laser alignment, the thermal compensation, and so on. So this is like a dream, but let's see if it will work out. But the most crucial thing is the GW interferometers. It's almost like a living being. So they are constantly changing and evolving as people adapt, and they change several things at the interferometer. So the agent should also change with time, which it seems to be a very tough problem, but we see a lot of developments in the recent years. So there are different ways to sort of combine different policies. One is called distillation. So what we would try to learn. So there are many ways to sort of learn a multitasking agent. People have tried, can we sort of share the neural network parameters across different tasks? It turns out it's not a very good strategy. The other one is can we have different rewards and then sort of weight all the rewards? That also seems to not work that well. So one other strategy is to sort of let's have different policies that we learn, but then let's try to also make sure that we also have a shared policy. So you sort of regularize our separate policies, but make sure that they sort of remain close to a central policy. And this seems to sort of help, at least in the literature that I checked, but we are trying to incorporate this. So before I sort of because in the interest of time, I also wanted to show some other stuff. The thing is, we at any of these interferometers, we have thousands, maybe even 10,000s of sensors of different kinds that are deployed, that can range from accelerometers or microphones, all kind of sensors. So, but the thing is, if you can sort of combine all this information, it can actually help. So it can actually help us improve the performance of the interferometer. So right now we use it, but in a human way, but we would like to combine it in a very so one application that was recently done is say this is our sensitivity of the interferometer, which I showed you, but then if you can engineer the photons and introduce squeezed light into the system, we can sort of reduce the short noise and then increase the sensitivity of the interferometer, as you can see in the green trace. And this is called squeezing, and it is continuously applied at LIGO, and to sort of beat the constraints imposed by quantum mechanics and Heisenberg's uncertainty limit. So what we see is it works, but we see if you look at the gray trace, that shows the level of squeezing that we can actually see. But we see that with time, it sort of degrades. And we are actually trying to see, because it's a complex optical system, we want to know what to touch to fix this thing. So what we did, like what not me, but Chris and Lisa and the whole team, what they did was they sort of used the auxiliary sensors that I showed you before, and then tried to build a model that is actually able to predict the level of squeezing that is changing. And by looking at the channels that help you predict the change, we can sort of see this is the subsystem, and then I can go and then sort of fix it. So this sort of work is being done. And I will sort of end with my last slide. It's like LIGO, like, so right now it's like the beginning of gravitational interferometry. It's just the beginning. We are looking for bigger and better projects. For example, the Cosmic Explorer is one such project. And LIGO, as you know, it has an arm length of 4 kilometers. But Cosmic Explorer will extend it to 40 kilometers. So it's a truly massive gravitational interferometer. And when you go to this sort of system, we would like to leverage AI and RL and all this kind of strategies. And yeah, so this is the last thing I can show. So if you want to see, so here you show all the neutron stars that we can capture. Here it's all the black holes. Let me just focus on the black holes. And the white trace, the O3, is what LIGO was able to detect. So this is like how it's a redshift. So like you are looking like to the edge of the universe. And then the LIGO has just captured, the inner circle of all these black holes. And with these bigger projects, we are aiming to capture way more stuff, which is now completely hidden. So this is the sort of merit that, like, the reward that we get from building such complex detectors. And then I think I'll stop here, take questions, and maybe I'll show this slide again, and then I'll take some questions. Thanks again for listening to my lecture.
Thanks, Nikhil, for the excellent talk. Are there any questions?
Yes.
You seem to suggest you wanted like one RL agent controlling all of the various different aspects of the thing. Why exactly would you need one if they're all well separated out in frequency space? I mean, you showed this very complicated plot at the beginning. Some of them are introduce noise at very different frequencies, so they would not really interact in terms of the like.
So some of them are separate in frequency, but there are many more that sort of share common ground. Say, for example, like we try to increase the circulating laser power, right, in our cavities. But when you increase the amount of light, it can cause thermal distortion of the optic. And the optic sort of changes its radius of curvature. So you have a thermal compensation system. So once you turn on the thermal compensation, it could sort of affect the level of squeezing. So there are all these subsystems that are sort of interconnected, unfortunately. So right now we sort of try to separate or like communicate between people and then sort of coordinate. But it would be really nice if an agent can supervise across these sort of tasks.
Okay, thanks.
Yeah.
Hey,
Hi.
I was curious about your software stack for like the last thing. So like, are you like creating like hardware that can do this in real time, or are you like using some form of like a low level system?
Which plot are you talking about?
No, I'm not talking about a plot. So in your last slide, right? Like
let's see. Okay.
Yeah, the question about like,
I
this
see.
Like, yeah.
Okay, this takes a bit of time. So here. Yeah, so we are looking at all possible solutions. So we want state-of-the-art software to train and deploy, possibly with cloud support, because these things we want to leverage GPU. But then we have our existing real-time Linux systems that sort of control the hardware. So we need to introduce we want some sort of solution which combines software and hardware with seamless integration. So we want both. And ideally, we want to actually increase the bandwidth. So probably we should leverage FPGAs at that point. So, but then it should also interface with all kind of sensors like image and then like all this kind of sensors. So it's a very, we are looking and probing different solutions that exist. Maybe it doesn't, we don't have one, we might have to customize something. So that's what we, yeah, that's our current situation.
I guess, I mean, it's fine if you don't know, but like I was curious about like the possible solutions that you're looking at right now. Like, are you looking at some form of like hardware core design kind of thing? I mean, you mentioned FPGAs, but like since that's a very like open thing that you're experimenting.
Yeah, so we have looked at NVIDIA target devices, which are not FPGAs, but like where you sort of you train and then you generate CUDA code and then you sort of deploy it to this Jetson device. So it's called Jetson. So that works. So we have checked that. We are also looking at Speed Goat, which is another sort of real-time hardware. We are also looking at possible FPGA solutions, but it's also like there might be a solution which will be very like, which will give you very good solution for one task. It might be very good at FPGA, but then it has to integrate with the existing softwares and hardware stack, and it has to also be real time. So yeah, so it's still, if you have some solution, I will be happy to. Yeah, please share with me.
Thanks for the talk. Yep.
Mm-hmm.
So this is very interesting. Sometimes at first when you do this kind of feedback,
Yeah.
You get improvement, but then eventually you reach a stage where you have to have trade-offs.
Yes.
Where maybe, often when you have these kind of control systems, you move low frequency noise to high frequency noise, or some. Right.
Yeah.
How far away are you from that regime? Is everything you're doing currently just better, or what are there other trade-offs like that to consider?
So yeah, it's like classic problem, right? Like when you have higher loop gain, you might introduce more sensor noise, right? So you can. So what we try to do, maybe I don't want to go back into my slides, but what I can actually go back here a bit. So let me see if I can get my. Okay. Yeah. So what we try to do is like we want like say 10 hertz to 5 kilohertz. That's like our bucket where we want it to be very clean. So we try to make sure that that's clean, and then we have all these control systems which will have like a bandwidth which is not crossing that thing. But then at some point we would introduce sensing noise, which will sort of determine the ultimate noise floor. Okay, so we sort of change the sensors and then like go to 24-bit DAC or like ADC, change the ADC, this sort of thing we constantly modify. But we are actually trying to push this barrier back and back. So we want to be more sensitive, but then how do you so how do you sort of push this low frequency noise floor better? So we have to get rid of all these controls noise, and yeah, so it's often a trade-off, that I would say. And so the problem is like now we were working, everything was fine, but now we want to push to the lower frequency, but then there is all this controls bandwidth that is sort of so how to sort of push it back but still maintain everything in lock and then observe. So that's a sort of challenge that we have, and many of it looks like many of the problems are coming because of our lack of knowledge in constructing very sophisticated controllers. Because of this complexity, we sort of compartmentalize, linearize, and try to tackle each problem separately. And that's the sort of motivation. Like if you can go for a MIMO non-linear controller, you might be able to do a better job.
there any other questions? Okay, we're about at full time, so let's thank Nikhil one more time.
Thank you. Oh.
All right, for the last talk of the morning session, it's wonderful to have Dee Luo here. He's an IAIFI fellow. He's been with us a couple of years, and he's going to tell you about many body physics meets artificial intelligence.
Yeah, thanks a lot, Jin, for the introduction. My name is Dee Luo. I'm currently an IAIFI fellow at MIT and Harvard. It's my great pleasure to share some of my recent exploration on many body physics and artificial intelligence. So to start with, I mentioned a bit my research interest is lying in this intersection of artificial intelligence, quantum information, and physics. Especially, I found that it's very intriguing and impressive. There's a lot of connection between physics, informations, especially quantum informations, as well as artificial intelligence. And one thing I always very curious is that with this recent year development, there's a lot of new design in artificial intelligence. People build a lot of large models, very fascinating optimizations and learning algorithms. But at the same time, as a very old subject, physics, but also has a lot of insights on nature intelligence. It tells us how nature works, what's the principle of the world. So one thing also very interesting is that how can this nature and artificial intelligence, they all bridge, enhance each other. So can we have a better design or understanding for both the nature and the artificial intelligence? And today I want to share some of the topics along the lines of AI for quantum many-body physics, AI for quantum optimizations, as well as some of the exploration on physics for developing AI. So to start with, I want to introduce this problem of quantum many-body physics simulations, which is a very general research topics ranging in many fields in condensed matter, high energy physics, quantum chemistries. But more generally speaking, there's like two categories of problems. Whenever there's a Hamiltonian is given that describes this many-body system in quantum mechanics, one can ask what's the spectrum of property of such Hamiltonian by solving the eigenstates. Or one can also ask the questions of real-time evolutions of a given Hamiltonian, which also have a lot of interest in physics related to chaos, quantum circuit simulation, dynamics of gauge theory, for example. But these kind of problems are actually known to be very challenging for two kinds of underlying reasons. One is that they have these very famous side problems, especially when there's a fermion on real-time dynamics. There can be non-positive real numbers or complex number appearings, which it cannot be described by the conventional probability distribution in classical machine learning. There's another very famous problem coming from the curse of dimensionality, where this Hilbert space actually grows exponentially, usually with this number of particles. And if one actually even asks GPT, he also recognized this challenge very precisely, at least from one perspective. He knows that this simulation of many-body physics is a very challenge because of the exponential growth of dimensionality. So people actually spend a lot of efforts trying to tackle these high-dimensional problems. There are many different perspectives. One very famous approach is coming from quantum Monte Carlo. And the high-level idea is to try to use sampling to detect some of the high-dimensional property. So, for example, if one want to get to some ground state property, one can get these imaginary time evolutions and use some of the techniques of Monte Carlo sampling. So this actually works very well, especially one of the famous examples is the lattice QCD community. Whenever there's no side problems, this approach can get to very precise predictions. But the challenge is that whenever there's a side problems, then this transition probability is no longer transition probability matrix anymore. It can have interference, and then it can cause the sample complexity, the scales, especially. Another very famous approach is coming from some of this tensor method under this name tensor network. In particular, the key idea here is to look for some low-rank tensor decompositions for high-dimensional objects. So one famous example is the MPS, matrix product space. So those kinds of methods are very efficient for low-dimensional systems like a 1D. But then there's still very open research for high dimension like a 2 or 3D, especially the entanglement grows a lot in those contexts. Another very encouraging and very interesting development in this day is the quantum computer. The idea is very natural because all these quantum worlds are very high dimension. So why not we just use a naturally high dimensional machine to handle this? So people have a lot of effort building both analog quantum computers as well as digital quantum computers. And they can be used to simulate both quantum dynamics, also can be used for some ground state problems. But there's also challenge because the current technology still face in this regime of the noisy quantum computer. So to get to high precision calculation, there's still need ongoing efforts. So today I want to discuss some of this advancement on this idea called neural quantum state. The high-level idea here is that actually can we use a neural network to represent such high dimension representation? So to give intuitive pictures is that let's consider m particle spin 1/2 systems, which is sitting on this lattice. So these systems actually have like a spin up and down, and one can actually view it as this the game of Go. You have these black and white chess. And then actually for this configuration of m particle actually is a 2 to the n possibility. In this sense, this wave function actually is a 2 to the n vector. So it grows exponentially. Then given this, we found this very encouraging progress in, for example, AlphaGo. You can find this very nice strategy of playing this game. One asks the question, can machine learning also look for what's the optimal spin configuration given these Hamiltonians? So earlier in, I think a few years ago, Khalil and Troyer, they first proposed this idea actually to represent this high dimensional wave function according to neural network. So the high level idea is that whenever there's some input configuration, one can pass the neural network and it output the wave function amplitude. And that's also somehow supported by this idea of a universal approximation, and hopefully one can have a compact representation for such high dimensional objects. And later, people also study more on the property of such a new quantum state, and it turns out there's a lot of very interesting and nice features. For example, it can get very high entanglement. Sometimes people call this Wannian law, and it can also have a representation for many different states. And then it can also be allowed to use in the variational simulation for problem, even there's a side problem, which is very hard for the conventional sampling technique. We also have some exploration recently with Jin also here, that we try to understand what's the supervised learning training behavior of such neural network, and we can show that by using this technique of quantum state neural tangent kernel, we can prove its convergence. And actually also very interestingly, we can engineer entanglement property of such neural network technique by using some of this quantum field theory technique of design neural network. That's also related to this NTK and NGP kernel. That's something very nice early in this week discussed. So since it's this proposal, there's also a lot of other explorations along this line. People talk about the representation powers and apply to quantum state tomography, also as well as the simulation of many body systems and quantum chemistries and dynamics as well. So today, actually, I want to talk a bit more on the symmetry perspective of this neural network quantum state. And the first thing I want to discuss is on the anti-symmetry neural network and the fermionic physics that we are able to study based on this development. So one of the key subjects of the fermionic physics is actually lying the Pauli exclusion principle. Or in other words, actually, it talks about this wave function has the property whenever it's changed the position of two electrons, it will change the negative sign. So this is a very non-trivial feature because if you just put a black box of neural network and it changes input, that you cannot get a negative sign out of it. So it means that it's not a naive or straightforward way to just have a neural network that fulfills such anti-symmetry property. So achieve that, actually, earlier we designed this idea called neural network backflow, which is inspired by the idea from Feynman in the early 50s, which he is using this idea to dealing with the helium problem. But actually, we generate this idea by further incorporate the machine learning advancement. So the spirit of the backflow actually is coming from the picture that usually in the material with some of our chemistry, we have the mean field orbitals. Those orbitals are good, I mean, have some physics picture, but they cannot capture the correlation effect. So people actually, to capture the correlation effect, they will put some first order question called threshold, and then there's a second question called backflow. And the key idea of the backflow is that instead of a mean field picture, one can have interacting orbitals. When the electron moves, this orbital also changes. And then this anti-symmetry actually is coming from this determinants of these orbitals. The key questions here is that how can one construct this interacting orbital to capture such correlative physics? So what we propose here is that instead of outputting a wave function directly, we are trying to construct the orbital from the neural network backflow transformation. So what it's doing here is that we have the configuration and input to the neural network, and then the network will output an orbital, which we call the neural network orbital, that modify the mean field orbital. And we can show that this orbital actually depends on all the configuration of the electrons, so it captures the many-body effects. And then we put this orbital into the determinant. And the anti-symmetry property actually can be guaranteed from such determinant, because whenever the determinant is changed to road, it will get a negative side out of such determinant. So we can actually show that such construction have very nice property, and we can further use it with this variational simulation scheme to lower the energy for such wave function and get the ground state of the problems. And we tested this on a bunch of very challenging model, including Hubbard model, Kagame model, and actually we achieved very good results compared and better than some of the state of the arts. So, yeah.
You keep maximizing distance to the microphone.
So one learning step put me further away from the microphone, but good. Yeah. So a question here in terms of the benchmarks, essentially, right? So you show these results. Can you say a little bit on how much improvement? Like, how should I think of these?
Yes. So some of these very challenging tasks of including these Hubbard models, which away from half filling, for example, in this 0.875 region, which know that have a very special size structure. And then we also compare this result with for some of this state of art, for example, DMRG, which is one kind of tensor network result. So we show that as the system grows, actually, we also approach this result very well. Another example is this called the Kagame lattice, of which people sometimes consider some of the spin liquid or whatever. That's also very challenging. Here we also compare to the ED result, and then we find a very nice this linear variance extrapolation, which is a signal that is very close to the ground state as well.
Thanks.
Yeah, thanks for the questions. And just recap a bit, I think the key message here is that this actually provides a way which one can develop anti-symmetry neural network and also allows one to change the size structure of these orbitals very directly. And actually, we can also theoretically prove that this scheme can be universal to approximate anti-symmetry functions and actually naturally realize this hierarchy called Slater-Drescher backflow hierarchy to make sure at least it's better than the existing hierarchies. And very interesting later, this idea was also further taken step by this very nice advancement in quantum chemistry under the Fermi net and Pauli nets. So that's also a very interesting article. They highlight the connection of this approach. So what is nice is that later the Fermi net and Pauli net, they actually also take this anti-symmetry idea, but generalize to the continuous space.
Yeah, so another question, sorry, about efficiency of these networks.
Yeah.
Practically how computationally expensive are they?
Oh, yeah. So that's a very good point. So the key complexity is coming from the one is the complexity of constructing this orbital. Another one is the complexity of taking the determinant. So basically, taking the determinant is scale is n to the 3 usually. N is the number of particles, and the construction of the orbitals. The complexity is coming from the neural network complexity. So it depends on the choice of the neural network. But usually usually the neural network complexity does not scale with n to the 3 because even for transformer, sometimes you get n to the 2 only. So roughly that's the complexity. Yeah, so to just also mention a bit more, people later also developed these very powerful techniques on Fermi net and Pauli net for quantum chemistry, which they incorporate the continuous symmetry and then use the determinant, also this neural network backflow idea to get the anti-symmetry function. And actually, they have also a lot of encouraging progress that go beyond the state-of-art methods this day. And recently, we also further extend this to quantum material, especially artificial quantum materials of this rate lattice. We also observe very interesting transitions from these Schrödinger atoms to molecules and have very interesting crystal field effects. So I want to go a bit more. I mean, besides anti-symmetry, I want to also discuss another very important symmetry in physics, which is the gauge symmetries. Especially this plays a very important role in the quantum field theories. So instead of just consider like an electron earlier in the many-body physics context, we also need to consider electron, generally the matter field coupled to the gauge fields. And such gauge theory plays a very important role in multiple contexts. For example, in the high energy physics, in the standard model, also in condensed matter, there's a lot of exotic matter physics that relate to gauge theory, like spin liquid or things. And it turns out in quantum information, the quantum error question can also be formulated as a gauge theory language. So that is very important, but we also know that there's a lot of difficulties of starting such theory. Particularly with the gauge field, usually it's a continuous degree of freedom. It has infinite degree of freedom, and you also need to obey a special symmetry, which is called the gauge symmetries. And then this theory sometimes can also couple to fermions, so we also need to take care of the anti-symmetry of the fermion simultaneously. And in particular, it's known that the fermion, because of the exchange statistics we just see earlier, it can create a negative psi whenever exchange two particles. So that creates also the very famous psi problems for fermions. So we know that previously people have a very powerful approach of the Lagrangian formulation of simulating this theory. For example, one is the path integral Monte Carlo, and also there's a very great development in the lattice QCD. And also in this week's talk by Dan and also Fiala's group's work, we also see a lot of very impressive advancement from the flow-based sampling approach. So all those approaches are very nice and fantastic, but at the same time, there's still challenge of the psi problem. In particular, when there's a psi problems, is non-trivial to just increase the speed of sampling. And there's also a lot of ongoing effort on the directions, but in general, this is a very open area. So today I want to also, instead of focus on the Lagrangian formulation, we can look into the Hamiltonian formulations where it can be used with other techniques. So under these Hamiltonian formulations, people explore this with quantum computer, which also can handle the psi problems, but it's have some limited power at this early stage. People also develop tensor network methods, but this is very challenging to include the infinite degree of freedom, for example, for gauge field, and also is subject to this limitation of high dimensional statistics. And today I want to talk about some of the exploration we have, which is along the line of the new network quantum state, and particular self the work. We first start with the discrete gauge theory of both abelian and non-abelian group. Later we generalize this to some coupling to fermions, and recently we further have advancement to the pure U1 gauge theory as well as the 2+1D U1 gauge theory coupled to fermion. So give a little bit more context of what this gauge theory look like. So the very simple gauge theory, let's start with the discrete gauge theory. So one example is the G2 gauge theory, which also known as the torical. So basically we have a bunch of this spin living on this edge, but that's a special gauge symmetry, which in physics people also call it Gauss law. So that's an operator we call AV here, which roughly speaking, these spins, they are not independent of each other. This spin configuration, they need to fulfill some constraint specified by this Gauss law operator. And then one can further generalize this G2 gauge theory to continued gauge theory. So one of the examples is the U1 pure gauge theory, which is the quantum version of the Maxwell like a E and N theory we know classically. And there, each of the particles on or this gauge field on this link actually is a U1 variable. It's an infinite degree of freedom. And again, it has a Gauss law, which we specify by this operator called GV, which means that these continued variables are not independent of each other. So one can take a further step, which is to couple this U1 gauge theory with fermions. So now on this vertex of this lattice, that's our matter field, which is labeled by this black dot. So now this matter field and the gauge field, they need to specify a further constraint together. And also this fermion have the anti-symmetry as well as the side problem. So some of our work to start with, to give a little bit more context here, is that let's consider this G2 gauge theory. So the language here is that we're some Hamiltonian, and the gauge symmetry can be manifest as a Gauss law operator we call GV. And then the GV actually is commute with the Hamiltonian H. So what we need to do is that we need to solve, for example, the spectrum of such Hamiltonian subject to this Gauss operator, which reads as GV acting on this side is equal to psi. So this is a symmetry constraint. In other words, can we construct a function psi such that the psi where this GV acting on configuration is equal to psi s? So the principle we take here is utilize this idea called equivariant principle, and that's also very nice talk by Tess and Robin in this week's talks. So the key idea here is that we can construct the invariant functions, which is invariant under these gauge transformations, and then we can also construct equivariant function which commute with this gauge symmetry operator. So one important feature here is that unlike, for example, the E3 networks or other, usually the symmetry we talk about in more classical context, which is the global symmetry, for example, globally translational symmetry or rotational symmetry, the gauge symmetry actually is symmetry acting locally. So we always have this index V, which is a vertex index, which means that every place is transformed differently. So one example to construct such gauge equivariant feature is that we can utilize the physics insight by this idea called Wilson loop or Wilson curve. So I'll omit some of the details here, but in short, in some of the work here, we actually propose a general framework to construct gauge equivariant neural network for quantum lattice model, which can be applied to both abelian and non-abelian discrete group, and also extended to the key-type DG models, the flat-tone ground state, as well as the toricals in arbitrary dimensions. And later we further generalize this to the continued gauge group. So we actually developed this for the continuous U1 pure gauge series. We also achieve very nice comparison compared to the existing method, which is the complex Gaussian method. And to couple this to the fermion, we actually developed another scheme which we use this gauge invariant and anionic symmetry autoregressive neural network. So the autoregressive neural network means that one can rewrite a function into some conditional functions. And actually this conditional function has some nice property because many of these gauge symmetries are local. So we can actually use the autoregressive construction to encode such local property. And this scheme is very general. It does not only allow us to impose gauge symmetry, but also to impose other algebraic constraints. So one example is the anion symmetry. So we know that for boson, there's a fermion, but there's also other exotic particle called anion. When you exchange these two anion, you're not getting a negative or positive one, but you can get a phase. So this scheme we can also utilize to compute like an anion central charge, which we have very nice agreement with the conformal field theory predictions. We can also use it to simulate the 1+1D quantum electrodynamics in real time. And we recently take a further step, which we can generate the scheme to the 2+1D lattice gauge theory, quantum electrodynamics theory, and finite density using this idea called flow wave functions. So here we are not able to deal with gauge field, which is completely U1 degree freedom without cutoff. We impose the Gauss law that coupled to the fermions, and also we can do sampling using the flow-based model directly. And in this context, actually, I have the psi problem, and it turns out that we can also simulate this theory even if psi problems. So we observe also a lot of interesting physics, such as spin breaking and confinements, charge crystal phase transition, and the magnetic phase transition using this approach. One more thing I want to talk about a bit. So previously, all the discussion on the lattice gauge theory, but actually we also have some attempt recently to go to the continued quantum field theory, which we don't have lattice anymore. So this is in collaboration with John, who is one of, I think, attended these workshops, and he also gave a talk earlier. The high-level idea is that we actually further propose a neural quantum field theory to continue quantum field, such that we can apply to many of these elite linear model, CS model, and the regularized Klein-Golden model, and achieve very good agreements with many of the calculations. So now I want to talk a little bit more on the next topic is, besides the ground state property I mentioned more earlier, we want to switch this context to the quantum dynamics. And it turns out this has actually a lot of connection to the high dimensional PDE research, which we also found very interesting, because while we develop this tool for quantum dynamics, it turns out it can also be applied to the quantum, the high dimensional PDE. So one question motivates this research at the starting point is that can we convert our quantum world as close as possible to a classical world? And the key idea observation here is that in quantum mechanics, we talk about wave functions, and then we talk about how it evolves through unitary or quantum channels. But then we also have a classical world, which the key object is the probability distributions, and then how it evolves maybe is following the stochastic process or a quasi-stochastic process. So what we are doing here is that we try to develop a serious scheme that to map our quantum world as close as possible to a classical world, such that many of these powerful tools in classical machine learning now can be utilized to describe our quantum world. So one of these actually can be realized is through this quantum tomography idea, which is called the positive operator value measurement, POVM. So this actually historically, philosophically, also very interesting, related to this idea called quantum Bayesian. So basically, when asked this question, whether we can get all the information of a quantum world through measurements. The standard projective measurement does not allow us to do that, but this POVM is possible. So basically, it says that once people do this quantum tomography use POVM, actually can convert the density matrix in quantum mechanics to the probability distribution without the loss of informations. So by utilizing this key scheme and idea, actually we develop a mathematically exact mapping to convert, for example, the very general Schrödinger equation, or actually here is the Liouvillean equations in open quantum systems to the probability differential equations, which the key object here is the probability P, and then in a high dimensional context, this actually becomes a high dimensional PDE. So now instead of solving the original Schrödinger or the Liouvillean equation, we can now solve a high dimensional probability differential equations. So to achieve that, we develop different scheme. For example, we can study the dynamics of such system by generalizing the standard low dimensional forward-backward numerical PDE scheme to high dimensional context by using like the stochastic optimization. So one scheme we developed is called the forward-backward scheme, which we can have a transformer to represent such high dimensional probability distribution at t, which we call the PT. And then we want to look for the future representation of such probability distribution, which we call the PT plus 2 tau. And then we can do a forward and backward evolution simultaneously and define the loss function that should agree at the place with t plus tau. So we can minimize this loss function step by step, and then to push forward this dynamics. We can also solve the steady state of such high dimensional PDE directly by minimizing the loss of this operator. So here, I want to also reveal a bit of the insight here is that by having this formulation, actually we can now view quantum particle as some kind of language, because they both now described by some probability distribution, especially it's a high dimensional distribution with long range correlations. So we also studied this in the context of quantum circuit earlier. But here, the key is that once of this formulation, we are now able to use very powerful machine learning tool, for example, transformer, to parameterize such high dimensional distribution of quantum particle. And this actually also can capture many important long range effects, as this paper say attention is all you need. Maybe you just need more attention to capture all these the quantum correlations. And then this also allows for exact sampling and inference as well. So it's very powerful. So we test this scheme actually on multiple different quantum open systems, and actually will achieve very good results, even better than some of the early work on the density matrix. By a restricted Boltzmann machine, we can do dynamics in 1D and 2D. Very recently, we also generate this to continuous variables by using the flow-based models. We actually call this idea called the Q-flow, which we use the generative modeling for differential equations of open quantum system using normalizing flow. So here, we also have a standard Liouvinian density matrix evolution by using this reformulation of the Husumi Q function in quantum optics. We are able also to convert the continuous bosonic quantum wall into a cosine probability wall, which looks like a classical probability distribution. And we use normalizing flow to solve these high dimensional differential equations. And also we achieve very good result, and even better than the existing method that one can handle. And we also found this very interesting to the ICML community. So this can be further generalized to other contexts as well. And one more thing we want to talk about is that actually we further also explore this idea. Just besides solving this time step by step, we may also ask the question, can we solve the whole space-time of such high dimensional PDE? So here we also developed this idea called the space-time neural network for high dimensional quantum dynamics, where, for example, to solve such Schrödinger equation, we have both space and time. Then now we can actually construct a space-time neural network, not just represent the state, but there's also an internal time network can represent the time. So now we can optimize the space and time simultaneously to get a space path for such PDE. So this is also something we found interesting and could be further explored as well. So this concludes a little bit on my this sharing on the physics and quantum many-body physics, especially with AI. So today, next, I want to just briefly talk a bit more on some of this AI for quantum on the perspective of quantum information science. So one thing we also explore is that there's a lot of topics, I mean, in these days. Yeah.
On the, sorry to slow you down on the previous one, but can you say a little bit more on the examples that you can apply this to and or have applied this to? So
which one?
Next slide.
Next one.
No, this, the space-time.
Yeah, so this one can be also applied to different like spin model dynamics, like Heisenberg model, transverse field Ising models, and so it's a very general scheme.
But in 1D and
1D, 2D, yeah, both are applicable. Yeah.
Could you just in this case comment again on the architecture quickly? I mean, it sounds like you're using a neural network to solve the time-dependent Schrödinger equation, which is very natural. What architectural choices did you make here that were critical?
Oh yeah, it's critical that here usually what people do is that they only for each time step they have a one neural network. This is also what we do previously, but now here actually we want to create a family of neural networks that also have the time dependence. So here, actually, what we do is that we have two networks. One is the external spatial network, which is the autoregressive network. In this case, we use the transformer. But there's another internal temporal network that specifies each time step what this transformer can behave. So that is something like we have a transformer, but then there's another neural network that outputs the way of the transformer to be time dependent. So now these two networks together becomes a space-time neural network together, can represent a family of neural network.
Thanks.
So this actually we also found have a this interesting connection to like this neural operator things in this context, because now we are not just solving a particular function, but actually a family of functions. So that's one thing we want to also explore. So come to this next topic of the content information. We actually also explored the different topics. One interesting we found is that there's a lot of interesting important problem in content control, where with the feedback information, the device is content, but the question is that can we come up with some nice protocol to control subsystem? So one question is that, for example, in the topological quantum computing context, people want to braid these particles, and the question is how to braid it actually is very open. So here we actually developed this differentiable programming technique to come up with very new protocol that people do not know before. Later we also find that this is physically reasonable by using the physics analysis. But today I want to focus on more one of the recent attempt we try to do for content optimization.
Real quick, can you say you said braid, right?
Yeah.
What braiding problem are you trying to solve?
Oh yeah, so in general we have this braiding of this anion on these things, which can allow us for universal quantum computing. But here we are not particularly solving the braiding problems, but instead is that when you braid this particle, you need to consider the context of the environment, the coherence. So you cannot braid too fast, because if braid too fast, you will destroy this particle, given there's a critical velocity related to gap of the system. Yeah.
I see. So the control problem is sort of how often to braid subject to the constraint of maintaining coherence.
Yes, the question is that the ideal case we want to braid adiabatically slow, but it's too slow, then it will be destroyed by the noise of the environment. We braid too fast, then it's destroyed by the physics. So we need to choose an optimal braiding scheme, like the speed of how to braid this particle, given the length and the time we have.
Are the specific braid actions sort of part of the action space, or is it just whether or not to braid?
It's on the action. So we have this phase diagram actually, which is related to the distance to braid and the time that allow to braid. So if we have a very long time, we can do like an adiabatic protocol. But the question is that if we have a relatively short time and long distance, what should we do? So this is an unknown question before. And then actually by differential programming, we come up with a jump protocol. Basically, we should move very fast and then make it to be roughly like a linear speed. Yeah, so maybe let me just...
As moderator, I'll just say you've got about 10 minutes, including questions.
Yeah. Is this thing not working? And maybe let me just briefly mention a bit on this several exploration we have. So one thing is on this content optimizations. So on quantum computer, this day people also develop quantum computer for many of these problems in optimizations. One interesting thing is that unlike classical optimization, people can do gradient calculation very easily, which basically based on this automatic differentiation and backward propagation, one can get like a O1 complexity. The content optimization is much more costly because what happened due to the measurements that you need to do like a parameter shift rule or something, which actually scale with the number of parameter, even when you take gradient. So that means that you are much more costly on quantum computer to take gradient. And the question now is that can we actually speed up such process? And this actually turns out to be a very interesting connection with the Koopman theory developed in the 30s. So in the old days, Koopman tried to ask these questions: can we solve classical problems using quantum mechanics? And then it developed this Koopman theory, which says that one can convert a classical nonlinear PDE to a high-dimensional quantum PDE. So this is the insight we have, because now this quantum optimization problem is also like a nonlinear PDE. So what we can do is that can we use this Koopman operator theory to lift this gradient quantum optimization problem to a high-dimensional space such it becomes linear. And once it becomes linear, then we can predict the gradient directly. So it turns out it's also a very interesting connections here with the quantum natural gradient as well as the quantum imaginary time evolution. So what happens that the high level idea is that for many of these quantum optimization problems, it can correspond to a quantum imaginary time evolution, which the long time limit it gives runs to this ground state. And it turns out this quantum imaginary time evolution actually is a dynamical system. So that also can induce something we call the quantum natural gradients, as well as this quantum fictional information. So now what I want to say here is that the Koopman operator theory actually can lift this optimization problem to this high dimension PDE in quantum imaginary time evolution, and that is also connected to the quantum natural gradient. So with this picture in mind, we know that this linearization of pretty gradient could be potentially happens whenever we have the quantum natural gradient as well as the over parameterization context. So basically what we do is that we can first collect a few gradients on the quantum computer, and then we put it to the common operator learning to lift up to a high dimensional space, and then to predict the rest of the gradient directly. And the prediction of the gradient is much cheaper than measuring gradient on quantum computer, because the prediction just need O1 verifications. So we test these schemes actually on multiple different regimes and with different optimization, and we found that it can achieve speed ups quite like a nice need for many of these contexts, from 10 factors of speed up to like a 200 factor speed ups, depending on different contexts. And we also apply this to many different systems, including quantum chemistry, condensed matter, and quantum machine learning to accelerate the quantum optimization, also using this idea of the Koopman learning. So finally, I want to also briefly share a bit on this physics for AI advancement. So what we recently do is on this generative models with physics process. So this is also in collaboration with Ziming, Liu, Tommy, Yishu, and Mestema. So here, actually, the key idea is that we have also very nice talk this week on like a diffusion models, and turns out this diffusion model is highly related to the heat equations, and there's also this recent development on Poisson float, which is actually related to the electrostatic. And then we ask these questions. There's also a lot of other physics PDE, for example, with the wave equation, the Helmholtz equation, the Yukawa potential Schrödinger equation. So can we all convert this different physics PDE to a generative model? So here we develop a general scheme and framework to converting and designing generative model from physics process. So one example here we analyze is the this diffusion model, Poisson equations, as well as, for example, ideal equation, displacement equation. So we come up with different criteria when this equation can be converted to generative model and what's the features they have. Another interesting exploration we recently have is that can we also design robots, planets, using the physics principle. And in particular, we're very interested in this thing called the multi-legged robots. So usually people like these 4-leg robots, they can run very fast. But in nature, there's also this multi-legged robot, like they have the 6-leg, which is the head support. We have the 12-leg with the centipede. So there's a lot of robot with a lot of different legs. And then the interesting thing is that once you have many legs, then your motion can have a lot of choice, because you can move your leg very differently. Right, so you have basically your choice of locomotion grows somehow roughly exponentially with the number of your leg. So that's actually very like the statistical mechanic or the spin model. So here we design a general like a spin model duality as a framework to study this robot planning of multi-leg context. And very interesting, you also discover new optimal locomotion protocol, for example, for this head support in the robot real robot experiment. So the high-level idea here is that we have this robot planning, and we have a mapping to the spin model, and then we can solve this spin model very efficiently now. And then, for example, we can get this head support forward motion. So this is a 6-leg robot, they can move forward. And we found that this in the experiment, it can come up with a new protocol that's better than the existing biophysics protocol. And we can also design robot that not move forward, but move sideways. It's very strange. It's like a crab or something, you move horizontally. Right? So this is called a side swing motion that does not exist before for head support, but we can also design such optimal movement using the statistical physics principle. Which is very new. So just conclude my talk today, I want to talk about this very exciting new opportunity for both AI and many-body physics and quantum information science. But at the same time, also there's very new opportunity for physics contributing to AI. So with the hope that we can also develop both artificial and nature intelligence together. Thanks a lot for the attention.
Other questions for Dee? Marisa, do you want to handle the back of the room and I'll handle the front? Well, that's not very fair, actually, looking at the distribution.
For the work that used natural evolutionary strategies, what made that the natural choice as opposed to some other sort of zero order optimizer?
Yeah, that's a very good question. We also try other zeros order methods like a similarity or annealings. It turns out the natural evolution here, I think, has a little bit more advantage by connecting to this natural gradient. It's like a noisy version of it. So we found that in practice, it's also have better performance than similarity annealing.
Other questions for D? D, could you pull up your GenFizz slide?
Yeah.
So it's kind of amazing how many papers you presented in this talk. I'm trying to, so this is a really interesting idea, and I'm curious what the little lock boxes mean at the bottom, and then how it correlates with the red X's and the green checks. I mean, which ones of these work? Do you have intuition for when some are better than others, etc.? I mean, it's sort of a natural idea, but I don't think I got many takeaways that I'm supposed to take away from which particular processes work and so forth.
Yeah, that's a very good point. Yeah, sorry for the brief mentioning on this topic. It's very interesting. I think zooming also in this workshop, people can also discuss. But together, we have a lot of ideas follow as well. But the long story short is that we have a special criteria in this work, especially we call the S-generative. This is only a subfamily of all these general model. And what this S-generative means is the smooth generative. So that means that we hold this generative model in the infinite norm regime, it becomes like a uniform or smooth distribution. So that's the criteria. So this yes or no is only saying whether this PDE can get to this smooth generative criteria. So the picture here is that because in diffusion model, when you go to very long time, you get back to this uniform noise, and this Poisson flow have the same picture. Here, by this green check or not, we're saying that, for example, if this Yukawa thinks that you are actually able to get this S-generated, this question mark is that saying that under some condition, the Helmholtz equation is able to do it, some condition does not. The Schrödinger equation, the wave, we put a cross there. It does not mean that it cannot be a generative model. It just means that it does not fulfill the S-generated. The reason is because the wave equation, unlike the heat equation, actually preserve information. Right. So that means that the information can translate infinite long, so it cannot be smoothed out. So that's the only meaning here. But actually, it's separate open questions, because even though it does not smooth out, it can still be used as a generative model, because you can change, like if a pool of water, you want to change one distribution to another distribution, you're still able to do so, even though they does not smooth out. So this all this what means is that there's the potential to unlock all these different equations. But we do have further, for example, very interesting example. We can actually to bridge this diffusion model and the Poisson flow together by interpolating these two differential equations into one, and that could also have some better performance than one of it.
Putting them into some combined model where they restrict to one or the other on a hyperplane.
Yeah, exactly. Yeah.
And is there a case where I should use Yukawa versus Poisson versus diffusion? Is there a sense of that?
Yeah, it's a good question. So the Yukawa here actually is very interesting because it introduced a mass, right, in the context where if you turn the mass to 0, then you recover one of these model before. So we also have a toy experiment to study that whether there's some benefit of including the mass on the Yukawa, and then it seems that sometimes it helps, sometimes it does not help. So it's still an open questions. Yeah.
Excellent. Well, let's thank D one more time.
Yeah, thanks a lot.
And Marisa, we resume at 2, is that right? Excellent. So, pardon? In here. So we'll be in here at 2, which gives you a full hour and a half to explore for lunch, go to restaurants, carry food back, whatever you want. Enjoy.
No, thanks.
But I think I have realized just how much you're doing the last year. It's great.
I think this is yeah, thanks. It's still very open. It's just the ask what's the property of different models.
But it's a very IAIFI question, and